Now let's talk about L'Hopital's rule. And L'Hopital's rule says that if you have the limit as x approaches some value of f of x over g of x, if that equals 0 over 0, or if that equals positive or negative infinity over infinity, then the limit as x approaches some value, let's call that a, of f of x over g of x is the same as the limit as x approaches that same number of the derivative of f over the derivative of g. So let's see how we can use that to evaluate limits. So here's the first one. The limit as x approaches 0 of sine x over x. So if we evaluated this limit, sine of 0 is equal to 0, and 0 is equal to 0. So this is going to equal 0 over 0. And usually, you'll, write off to the side, like something like that, just to state that you're using L'Hopital's. And so that's going to equal the limit as x approaches 0 of the derivative of sine of x is cosine x, and the derivative of x is 1. And now we do the same thing, we just evaluate the limit. Cosine of 0 is 1, so we get 1 over 1, and that equals 1. So the limit as x approaches 0 of sine of x over x is equal to 1. So let's go ahead and do another one. So we have the limit as x approaches infinity of log x over x. Once again, if you evaluated this, log of infinity is infinity, and infinity is infinity. So we get infinity over infinity. And we're going to use L'Hopital's because it's infinity over infinity, and that's one of these. So what we're going to need to do now is we're going to take the derivative of the numerator and the denominator. So the derivative of log x is 1 over x. The derivative of x is 1. And now we're going to evaluate this. So the 1 over infinity is 0. And 0 over 1 is 0. So the limit as x approaches infinity of log x over x is 0. So, and not all the times when you get infinity over infinity will you get 0. And not all the times where you get 0 over 0 you'll get 1. It really depends. And now let's go over an example where L'Hopital's isn't appropriate. So we have the limit as x approaches 0 from the positive side of log x over x. So if we evaluated that, well, on top, log of 0, or log of x as x approaches 0, is negative infinity. Because remember, a log kind of looks like that. So as you get closer to 0, the log goes to negative infinity, and x is going to go to 0. So what do we do from here? Well, if we did L'Hopital's, we'd get a completely different answer than if we just thought about this. Well, we have a negative huge number over a positive tiny number. Well, a big number over a small number, that's going to get really, really big. So this is simply just going to be a negative big number that's getting even bigger. So it's even going to be bigger than this infinity because we're dividing by 0. So it's just going to be negative infinity. Because this 0 isn't really 0. It's the limit as x approaches 0. So it's not undefined. It's negative infinity. If you would have used L'Hopital's, you would have gotten something completely different. So you got to make sure that you're using L'Hopital's when it's appropriate. So now let's do one more challenge problem. So the limit as x approaches infinity of 1 minus 1 over x to the x. So if you just look at it now, I mean, you can't really see something, a numerator and a denominator. It's not a quotient. So this again is a challenge problem and something that I'm not really sure if you're expected to be able to do something on this test, but we're just going to call this L. So what's really bothering us at first is this power, the power of x. Because if we evaluated this, we get 1 minus a really small number to a really big power. So we don't really know what this is because of this big power. So we want to get rid of that power. So what we're going to do is we're going to take the natural log of both sides. So we have the natural log of the limit as x approaches infinity of 1 minus 1 over x to the x, and that's going to equal to the natural log of L. And from here, we can use a property of limits, which is that the log of the limit is going to be equal to the limit of the log. So this is equivalent as saying the limit as x approaches infinity of log of 1 minus 1 over x. And that's going to equal log of L. From here we can use a log rule that says that log of a to the x is equal to x log a. So limit as x approaches infinity of x log of 1 minus 1 over x equal to natural log of L. And from here, what we're going to do is we're going to rewrite this. So this is going to be a step that you're going to be using a lot with L'Hopital's, which is that if you get an expression like this, x log something, or x times, or two different terms. So you have, in our case, we have an x and a log 1 minus 1 over x, and we can't evaluate it because we get infinity times log of 1, which is 0. So we can't evaluate this. So what we're going to do is this x, we're going to rewrite it so that we get a quotient being, a fraction. So this is going to be equal to the limit as x approaches infinity of natural log of 1 minus 1 over x all over 1 over x. So dividing by 1 over x, that's the same as multiplying by x. So this step right here that we took from here to here is something that you guys are going to want to remember, because even though this question in all is a pretty challenging problem, this step is something that is a method that you guys can use a lot to help you reach a point where you can use L'Hopital's. So dividing by the reciprocal is just like multiplying. So from here, now we can evaluate this limit, and we get log of 1 minus 0, which is 1 of log, well, if we evaluate this limit, we get log of 1 minus 1 over a big number. 1 over a really big number is 0, so we get log of 1. Log of 1 is 0. So we get 0 in the numerator, and then on the denominator we get 1 over a really big number, which is also 0. So we have 0 over 0 equals log L. So here we can write down that we're using L'Hopital's, and we take the derivative of log of 1 minus 1 over x, and we get that the limit as x approaches infinity, and this is kind of a chain rule one. So first we take the derivative with log of something of this variable, which would give us 1 over that thing. So 1 over 1 minus 1 over x. And then we need to multiply that by the derivative of this inside part. The derivative of 1 minus 1 over x, well, that's just going to be 1 over x squared, because we're looking at the negative 1 over x. That's the same as negative 1 as negative x to the negative 1, and the derivative of that is x to the negative 2, which is 1 over x squared. The denominator, derivative of 1 over x is negative 1 over x squared. And that's going to equal to natural log of L. And if you can see what happens next, these terms cancel out. We have the limit as x approaches infinity of 1 over 1 minus 1 over x, and don't forget the negative sign that was from the denominator right here. That's going to equal to natural log of L. And at this point we can evaluate the limit, and we get that if we plug this x equals infinity, 1 over infinity is 0, 1 minus 0 is 1, so we get negative 1 over 1, which is negative 1 equals negative 1 equals natural log of L. And L is equal to 1 over e. You could just take e to both sides, and you'd get, e to the negative 1 is equal to e to the natural log of L. And then, this side turns into L, and e to the negative 1 is 1 over e. So, that's how you use L'Hopital's. Once again, that's a pretty challenging problem. And, the first couple steps are ones that I don't know if they would expect you to be able to do right off the bat, off the top of your head. But right here, this is where the big step happened, where we rewrote x as dividing by 1 over x. And that's something that you guys are going to need to remember and use in the future. That's L'Hopital's.